and put another static charge here, it would experience a force due to this guy's force field. And it would experience a force this way. If I brought over a negative charge,
there should be an eraser.
And I place the negative charge here, we know what this red electric invisible field would do. It would put a force in the opposite direction. So the electric field lines always show what a positive charge would do, and we know that the electric field would put a force on a negative charge, placing it in the opposite direction. You know, people say, Mr. Sosinski, what do you do? I'm a teacher. People ask force fields, what do you do? I put forces on other static charges. That's what they have to say. That's their job. This invisible force field puts forces on other static charges, yes? Now, this isn't the only kind of force field. This is called an electric force field. You could apply this same principle to the force of gravity. If you have a mass, just by the presence of that mass, somehow or another, the space all around it here is altered. There's an invisible gravitational force field there. Of course, it doesn't look like that yellow line. If you wanted to visualize this gravitational force field, what you do is pretend to place a tiny imaginary mass which I refer to as Timmy or Tim. You place Tim here and you say, hey, if Tim was free to move around, how would Tim respond to the invisible gravitational force field around the mass here? Well, of course, it would be attracted. If I place Tim here, it would be attracted. I place Tim here, it would be attracted. I place Tim here. So I get a visualization of the invisible gravitational force field. Sometimes you're asked to solve for the gravitational field strength, yes? Well, recall we had that formula Fg equals m times g, where g is the acceleration due to gravity. This little g here could also be thought of as the invisible gravitational field strength. The acceleration due to gravity surrounding a mass is equivalent to the gravitational field strength around that mass. Well, now we go back to magnetism. If I have a magnet with its north pole and its south pole, and I'm sure you played with like little bar magnets, you could bring one bar magnet up to another bar magnet and you could get the other bar magnet to be like repelled away without even touching the first bar magnet to the second. It's so cool. What is actually pushing it away when the first bar magnet isn't really, making contact with the second one? Physicists say there's an invisible magnetic force field around every magnet. Of course, it doesn't look like that yellow line. And right now we're going to learn how to visualize the invisible magnetic field. Now, when we were studying gravitational force fields, what did we pretend to place around the mass? A little baby mass, a tiny imaginary free to move mass. When we were studying electric fields and we wanted to study the field around a static charge, we studied what a tiny imaginary positive charge would do. Well, now that we're studying the magnetic force field around a magnet, guess what we're going to pretend to place in the space around the bar magnet? A tiny imaginary magnet. But this tiny imaginary magnet is a free to swivel tiny imaginary magnet. And of course, tiny imaginary free to swivel bar magnet. And basically, what is a free to swivel bar magnet called? People carry it around to help them out in the woods. Yeah, it's a compass. So basically, a tiny imaginary compass. Yeah, a tick. Like, pull it off your arm like you got Lyme disease. All right, anyway. So if you placed a tiny imaginary free to swivel bar magnet, a little tiny compass, it would swivel around right here, yes? And let me make this a little bit bigger here. It would swivel around right there. That little point there in the middle is the pivot point, which is that little tiny free to swivel bar magnet would swivel around. And which way would it come to a stop? Which end of the bar magnet would be right over in here? That would be the south pole, yes? Because opposites attract, and it would be attracted to this big north pole of the bar magnet. So this would be a little baby south pole, and this would be the north pole, the little free to, you know. And it turns out that whichever way the little tiny baby bar magnet's north pole is pointing, whichever way the little tiny bar magnet's north pole is pointing, that's the direction of the invisible magnetic field due to the big pop-up bar magnet here. So we know then if that little compass is pointing that way, then the field line, the magnetic field line, is kind of going that way.
Is it curved or straight?
It's a little bit curved. If we placed the tiny imaginary free to swivel compass, or bar magnet compass right here, okay, which side would be like over right here, Samantha? That would be the north, yes? So this would be the south. And whichever side the north pole is on, that's the way the compass needle is said to be pointing. Therefore, we know the magnetic field there would be going like that. Compasses always point north when they're not near other bar magnets, when they're only experiencing the Earth's magnetic field. But when they're brought into the presence of other bar magnets or other magnetic fields, that new magnetic field overpowers the Earth's magnetic field. Now, this next one's kind of tricky. You might just want to kind of watch and not draw these things. But let's say I put a compass right here. Yes? Now, due to this south alone, due to this south pole alone, the compass needle would end up pointing like this. with a north like this, and it would be pointing this way, yes? But due to this North Pole up here, the compass needle would end up pointing that way, with the north being repelled from this north, yes? But both are there at the same time, and when both are there at the same time, it's kind of like the resultant force, yes? So guess which way the compass needle ends up pointing? Not this way, not this way. I heard somebody say it. It ends up actually pointing down, like this. And if we kept playing this game for all the points around the bar magnet, this is what the overall magnetic field around the bar magnet looks like. It goes out, loops around, goes in, and actually goes through the bar magnet to make a complete closed loop. So far, we haven't studied field lines that make closed loops. That's what distinguishes magnetic fields from electric fields and gravitational fields. Gravitational fields and electric fields never make a complete closed loop. Magnetic field lines always make a complete closed loop. If we played the tiny imaginary compass game and we placed it on the other side, you would get the same overall shape, where the field lines come out of the North Pole, come around, down, back into the south. And as all field lines, magnetic field lines never cross, never touch each other. So be careful not to have them touch each other or cross. Sometimes they go off your page and come back on, but that's okay. And that's a visualization of the invisible magnetic field around a bar magnet. And remember how we said when the field lines are closer together, that's where the field is the strongest? So where's the field going to be the strongest? Yeah, at the two poles, at this end, this end. That's where, look, whoa, the spacing's really close. Out here, the spacing isn't, as close together. Shira.
In the Earth, though, isn't it like that one, the way how you have to curve in and there's this, the space is not underneath the part? Because I'm not wondering.
No, with the Earth, that's still the So the invisible magnetic field around the Earth looks like this. And remember, the Earth's like a big bar magnet that has its North Pole down south, and it has its magnetic South Pole up north. So the field lines come out of the magnetic north up to the south. And that's why if you have a compass and you're in the woods over here, which way does the compass needle point? Up towards the geographic North Pole. compasses always point in the direction of the invisible magnetic field they're placed in. You might be thinking about this, Shira. I remember hearing how, like, if you were navigating by a compass, yes? And of course, like, if your compass was, like, right here, you know, it would be pointing up that way, and it would be taking you towards the geographic North Pole, yes? But if you ever happen to stumble right here above the actual magnetic pole up there, and you're holding your compass flat like this, so there's your little needle, you know, pivot point, you know, like flat like that. Well, which way does your compass want to point when it's right there on smack? You know, I'm holding it flat like that. This is my hand. Yeah, it wants to point down. Yes? It wants to point down because it's attracted to that pole right there. But if you're holding it flat this way, it can't move down. So guess what the compass needle ends up doing sometimes? Spinning. Yeah. You know, well, at the magnetic South Pole, which is really close to the North Pole, not quite. So, you know, they say, oh, it'll have you going in circles, you know, because it'll just be spinning. But as far as the strength of the field, whoa, that's where it's strong compared to out here, just like a bar magnet. All right. Now, it turns out that bar magnets aren't the only things that have this invisible magnetic field around them. What? It turns out that if you have a wire that has an electric current in it, there's an invisible magnetic field around that wire. No current, no magnetic field around the wire. Again, human curiosity never ceases to amaze me. Yeah. Somebody monkeying around with little baby electric circuits, like Oersted or Faraday. They happen to also have a magnetic compass near it. And they notice that, oh, look at this, look at this. When the current is off, the compass needle lines up with the Earth's magnetic field, points towards the geographic North Pole. But then when they hit the switch and turn the current in the wire on, the compass needle would switch. No way, no way. And then, of course, if they turned the current off, the compass needle went back and point it and line it up with the Earth's magnetic field. So this was like the first evidence, oh my God, you put the current on, there is this invisible magnetic field around wires that have a current in them. So let's say this is the wire right there that you're dealing with, yes? Well, the invisible magnetic field around that wire, if I placed my hand compass right here, yes, the compass needle would point that way. If I put my compass right here, it would point this way. If I put my compass needle right here, it would point that way. And if I put it right here, the magnetic compass would turn this way. It turns out that the magnetic field makes like a closed donut around the wire with the current in it. Kind of like this tape right here, you know. Not fat like that, but like you imagine a line just like the tape. And that's when I'm going to attempt to draw right here. This invisible magnetic field, like this. So wires with current in them have a field, and what you do is you can kind of like make it look three-dimensional by showing the invisible field going in front of the wire, but then not showing it go behind the wire, like this. So this red line represents a magnetic field, not around a bar magnet, but around a wire with electricity. And in front of the wire, the magnetic field goes this way, because that's the way the compass pointed. Over here, it goes this way, then that way. And of course, it's not just there, it's all around the wire. So I could draw this over here as well. And then over here as well. Now, this becomes tricky because, focus in here, people. These are three-dimensional diagrams that we're drawing. And essentially, folks, if somebody asked you, what is the direction of the magnetic field at this point right here in front of the wire? Out in front. So this pen is my wire. And I said, this point right here, what is the direction of the field? Well, from the way you're looking at it, the direction of the field would be to the right. So that blue point there, the direction of the field would be to the right. And of course, that green point behind the wire there, you know, it's actually behind the wire over in there. You know, that would be like, back here behind the wire. What would be the direction of the invisible magnetic field back there?
Left.
To the left. But here's where it gets a little new, like some new terms we're used to, like left, right, up, and down. But if you wanted to describe the direction of the field right here, at the side right here, well, it's kind of going this way, yes? So a popular way of describing that is into the page or into the board, that way, yes? And if you wanted to describe this point over here, what's the direction of that invisible magnetic field? Yeah, out of the page. Now, the AP also likes to indicate these directions with a XYZ axis, yes? So you have X this way, and that's called the positive X-axis, yes? And then, of course, if you go that way, you have the negative X-axis. If you go up, that's called the positive Y-axis. And if you go down, that's the negative Y-axis. you were going into the page, yes? And I'm going to try to draw this, that way, into the page. That might look like a 45 this way, but I'm trying to draw like into the page, make my diagram look three-dimensional. That's positive Z, and out of the page is negative Z. The symbol for into the page is a circle with an X through it. The symbol for out of the page is just a plain circle. So if you were going to do it in terms of this method, what would be the direction of this blue right here, the blue dot right out front? Positive X. What would be the direction of the green in the back? Negative X. What would be the direction of that yellow there over on the right side of the wire? And what would be that black point on the left? Now, it turns out, folks, if the current changed direction, and I don't expect you to touch your notes, so don't you change your notes to get too messy, but if the current changed direction, yes, and was going this way, the magnetic field has the exact same shape, but guess what happens to all the orientations, all the directions? They're in the opposite. So all these directions would be like this way, this way, this way, this way, just in the opposite. Why? That's just what a little baby magnetic compass does when placed there. It's fundamental. That's just what a little bar magnet does when it places. You have the current run down, you put the little baby mark bag right out here, it points that way. And you're expected to be able to figure out which way the fields will be going, so that if you're given this diagram like this, weeks from now, and you're told the current is going up, and you're asked for, hey, this point P on the side, what's the direction of the magnetic field? You're supposed to remember which way it goes, depending on the current and all. But there's good news. There's a right-hand rule. It's the first of 4 right-hand rules that help us figure out little magnetism things, yes? And this is how the rule goes. If you take the wire and you grab it with your right hand, yes? And you make sure your thumb is in the direction that the current is going. Whoopsie. Your fingers curl around the wire in the direction that the magnetic field happens to be pointing, as shown by a little compass needle placed there. So basically, at point P, what is the field going to be doing? Coming out of the page. Yeah. And over here on this side of the wire, what would it be doing? No, not into the page. And around back, it would be going to the left. So another way of showing this is by using the X's and the O's. Over here on the right, what was the field always doing? Coming out. And what was the symbol for coming out? Circle. So over here, we could draw circles. And over here, charge going in, sometimes it's just x's too, or sometimes it's a circle with an x. So let's make a note of right hand rule number 1. Grab wire. Grab hand. That's funny. Grab wire with right hand and thumb in direction of conventional current. I'm running out of room there. I'm just going to come up top here. Fingers curl in direction of the field. The fingers curl in the direction of the invisible magnetic field. Okay, we'll stop there.